All right, welcome. Today we're going to talk about chapter 7 of the book. So this chapter talks about last time we talked about backpropagation, and so that's an algorithm that lets you update your weights. But in order to do that, you need to know the gradients. And so this chapter talks about how you actually calculate those gradients, and then it also talks about initialization. Uh, this chapter was way more mathy. I didn't find as much intuition in this chapter, so uh, for what it's worth, we'll kind of go through this, but I'm not sure if you guys have questions, happy to answer them, but I'm not sure that I'm going to cover it in the level of detail that the chapter goes through things. All right, so using the professor's slides here, and um, if you recall, what we're talking about is we've got some sort of supervised learning problem where we have ground truth labels. We're going to take an input, we're going to have some sort of model, we're going to make predictions. So based on this, we're going to have some loss function defined, which compares our predictions to the ground truth labels. And we saw, like, for real numbers, it could be mean squared error loss. For categorical data, binary classification, it could be cross entropy loss. Um, so we just have this notation: big L is some function that compares our predictions to the actuals, and the farther they off are, the more we're penalized. So here's a sample neural network. Not going to really go through this slide, but the idea is you calculate in this diagram everything from left to right to make your predictions. And then the backpropagation algorithm, sorry, gradient descent algorithm says that we're going to update our weights, these hidden parameters, based on whether bumping them up or bumping them down will lower the loss. So ultimately, the problem we have then is we need to know, should we bump it up? Should we bump it down? Should we bump it up a lot or a little? Okay. And that's based on the gradients. So in the regular two-dimensional world where you have a line, then the gradient is just the slope of the line. All right. Um, uh, a steeper, more vertical line is going to have a higher slope, a higher gradient, and a line that's closer to horizontal, closer to flat, is going to have a smaller, lower gradient. If you have a curve instead of a line, what we're really just talking about then is the slope of the tangent line at any point on the curve. So it's really sort of the same thing as a line. We're just dealing with, at that tiny little point on the curve, it looks like it's sloped this way. Again, steeper, more vertical, steeper, means that for a small change in your variable x, you're going to have a very big change in your output. And so that's why the gradient's bigger. When you have a horizontal line, then that's when you have the smallest change for a given change in your input. Oh my goodness, so many windows to manage. Hold on a sec, guys. Uh, Lost my mouse. And in the extreme, if you have a horizontal line, then the slope is 0 and the output value does not change at all, no matter how much you change your input. And so then you would have no gradient. You would have a gradient of 0, effectively no gradient in that situation. And that's kind of accurate because nothing you do to change your input is going to actually change the value. It's not going to change your loss if you have something that's perfectly horizontal. All right, so we've got a whole bunch of notation and we're going to have more slides. We're not going to go through all the slides in detail, but the idea is that the loss is just the sum of the losses on each of our training examples. So we're going to sum up, and I here is all of your different training examples. All right. Our gradient descent algorithm says our parameters from the last time step, we're going to take a small number, like 0.1, 0.001, times the gradient of our loss function with respect to all of our parameters, our hidden parameters for our neural network. Okay. Um, and we're going to subtract that. So we're going to push things towards smaller loss. And of course, this little push is not going to necessarily work perfectly. This is an iterative algorithm, and over time, what you hope is that this algorithm, the little deltas that we're accumulating are going to accumulate, and they're going to accumulate in the right direction. And so what that will do, like we talked about, is it'll get us to a local minimum of our loss function, and hopefully it's a pretty good minimum. There may be multiple local minima, but hopefully this one is the global minimum or at least very close to it. So if you look at this previous diagram here, the notation that we're going to see in this chapter, let me see if I can go back one slide here. Uh, yeah, it's not that hard to, it's not that easy to see, but basically the weight matrices for each of these nodes is going to use um, the notation capital omega, and then capital omega, like sub 1, sub 2, sub 3 has to do with which layer. And then the equivalent intercepts or biases, those are going to get the Greek letter beta. All right. So basically they're saying, hey, here's our list of our whole parameters. And if you compute, this is multivariable calculus stuff, okay? You compute the partial derivative of the loss function with respect to, say, beta 0, okay? That would be this thing. Then basically that tells you if I increase beta by 1, how much is the loss going to change? Okay. Question in the chat. Is gradient variable to control undershoot, overshoot? Seems like the function will depend on timing constraints and how much of delta we're comfortable. Yes. So in the SGD algorithm, we're going to have this learning rate. Sometimes people use lambda. In this case, in the book, they're using alpha. And so you're generally going to take a small step because you don't want to risk overshooting. What's the definition of small? That's not, there's no absolute science to that, okay? But what people can say is that if you sort of scale your inputs to be on the order of variance 1, okay, then something like 0.1 or 0.001 does tend to almost always be a fairly small step. Ultimately, what people tend to do on a very novel problem is they'll just experimentally test it. So they'll say, what if I set alpha to 1, 0.1, 0.01, 0.001, 0.001, and just see. And then based on the behavior, which kind of we get into next chapter, you can see whether you possibly have some overshoot behavior, or if you have the reverse, where it just seems to be learning, but so super slow that it's taking forever for it to sort of work its way down. The loss function is decreasing, but super duper slowly. So something like that, where you just use like a logarithmic scale, you can fairly quickly identify what range of learning rates seems to be reasonable. Because again, you're not training it to convergence; you're just training it early on to see, hey, with 0.1, I got some really erratic behavior. With 0.01, it seemed reasonable. 0.001 was good, and then like 0.0001, it seemed to be working but super slowly. So then that kind of tells you to narrow it down right there. All right, so a lot of the rest of this first half of the chapter about gradients is really all of this partial derivative stuff. And so I think what I want to focus on is a little bit of the intuition, and then I'll see if you guys have any questions about the actual derivative stuff. So they're saying like, yes, if you looked at that neural network we were just looking at with, I think, 3 hidden layers, you can write it as a big equation because you're doing multiplication and adding of biases and whatnot. But it's a real problem-sized neural network is going to be a very huge equation. So how do we want to do this in a more practical way? So trying to find the next. Okay, yeah. So this next set of slides I think is pretty useful. So first we're going to talk about the forward pass, which is how we calculate our prediction outputs. Okay, so our inputs come in, and so for example, if you look at this second node here, all right, it's going to send its output to both nodes on the next layer, but we can in particular kind of look at um, uh, the path from this node to that node. And ultimately, what you can do is you can count up all the paths. I mean, it'll get to be many, but you can see like each node, which nodes it affects, and you can watch things go kind of from left to right in the forward pass. All right. So if this node over here has a weight of 2, then basically whatever comes out of this node, it's going to double it. And so you can imagine that, like, if, again, oversimplifying, but if this node just always doubled it, this node always multiplied by 5, and over here we always multiplied by 3, 2 times 5 times 3, basically that's 30, that whatever the output from this node originally, what's going to make it out here is going to be 30 times bigger than whatever we output over here. And again, I'm oversimplifying. I'm not dealing with some of the activations and some of the other complex stuff, but just at a high level, that's what we're kind of looking for. If instead of multiplying by 2 and 5 and 3, if it was multiplying by 0.1, 0.01, right? Then what you're now talking about is, oh, okay, what's going to come out here is going to be like 1,000th of what was here. So that's really what we're trying to see is how much does changing the output of this node affect our eventual output and our eventual loss. All right, so I think we have a few slides here. This is a diagram that was in the book. So when we're calculating the backward pass, what we can do is instead of going from left to right, we can go from right to left. So how does this particular hidden node here affect the loss function? What you can see is there's only 4 ways in which it sort of affects it. Or rather, the weight contribution from this node to this first node, there's only 4 ways in which it affects our loss, because it has 2 outputs here, and then each of these, you calculate the loss and you sum it up. Okay, so if you kind of understood what was happening on these 4 paths, which we're not going to get into the gory details yet, but if you did know kind of how much, then you could say, okay, I understand exactly how much the contribution on this, I don't know what to call this, bright orange brick colored path, how much this particular value contributed to our loss function. But once we've sort of figured this out, then what we can do is we can kind of keep going further backwards, further to the left. And so we can say, hey, the contribution from this node, okay, is going to be these 3 things over here, and then how they go forward. But you'll notice that one of these 3 things is exactly this thing that we were talking about before. So if you calculate all of the different contributions at a particular level, then when you go to the next level, you kind of have all those, and you only really need to add one more step to calculating how much something earlier contributed. And then we can do this again, where we can go one more step to the left. And so now, talking about on this very first pathway, what are the things it affects? Well, up here, this goes to both those nodes. But again, the idea is that now, on the previous slide, we could have calculated all of these different effects here. There's 6 arrows here. We could have affected sort of the effects of all 6 of these. And again, I'm purposefully avoiding using calculus terminology here. I'm trying to keep this like lay. For those of you who know the calculus, that's great, but I'm purposely avoiding that. We can get into the formalism. But so the idea is that you might know that this effect up here is very big, and this effect down here is very small. And if you know that, then you can actually work that backwards to say that, okay, these effects, if the weights are similar, this top effect is going to be much bigger, and this bottom one is going to be much smaller. And so you can actually propagate that information backwards, and that's why ultimately it got nicknamed backpropagation. All right, so that's the sort of high level intuition. Let me pause here and see if there are any questions about what we've talked about backpropagation. There's going to be a whole bunch of slides, and I think I'm going to touch on some of them, but not necessarily too heavily. Any questions? All right, so I've been doing it a little bit hand wavy. Here's some more formal math. All right, so the toy example that he gives, there's none of this business of multiple nodes, okay? So this greatly simplifies things. We have a complex function, but we're only talking about just real numbers, scalars, okay? There's no vectors, there's no nothing, okay? So if you have an input x, what are we going to do? We are going to multiply it by a number and add another number, and then we're going to take the sign of that result. Then what we're going to do, we're going to multiply that by a number, we're going to add a number to it, and we're going to take e to the power of that result. Again, this is still just a real number. Multiply it by a third weight, add a third bias, and again, just a real number, and take the cosine of that. And now we have a fourth weight we multiply that by, and a fourth bias that we add. So this is fairly complex, but again, this is just this is not vector calculus. You can solve this with just regular calculus because this is just single variables. Okay, so if you were calculating this, like if I said x equals 1, all right, if you're doing this on a calculator, what would you do? Well, if you knew what w was 0 is, right? Let's say it's a half. So then you do 1 times a half, you do 0.5. If the first bias, beta 0 is 0.1, you add 0.1 to 0.5, you have 0.6. And then you punch on your calculator. What's the sign of 0.6? You get some number, you multiply by this, add that. You could just manually calculate this on your calculator. And how you would do it is you would do it sort of from this innermost to the outermost. And x only appears once. So this is a relatively simple function. So in this case, question in the chat about like activation functions. Yeah, these are not necessarily realistic activation functions. We're trying to do is just a toy example where we're doing a series of calculations. And what we want to show is that we can calculate how much W0, beta 0, or sorry, these are omegas, omega 0, beta 0, how much each one of these, omega 1, beta 1, how much each of our parameters influences the final output of this combined function. All right. So this is, yes, this is not a very realistic example for network, but the idea is we just want to show, without getting into vectors yet, so for those of you who are just familiar with regular functions, maybe calculus, that we can basically see how much, for any given input x, how much these different weights influence the output of our function. All right. So in calculus, if you guys haven't taken calculus, the derivative of a sine function is the cosine. The derivative of e to the x is e to the x. It's unchanged. And the derivative of cosine is negative sine. So if we know these three derivatives, okay, then basically we can calculate the derivatives of this whole expression, and we'll do it step by step. So what we want to know ultimately I'm going to read it from left to right. Okay. So our loss function, again, is we're going to use squared error, is prediction minus actual value squared. And by the way, you might have seen it written as actual value minus prediction. It's the same thing once you square it. Okay. So how much does our loss function change based on this first parameter, beta 0? So if we increased beta 0 by 1, what would happen to our loss? So if we say this derivative, and by the way, we're only talking about nearby, like in the neighborhood of our actual values. Okay, obviously it's a curve, it's not just going to be a straight line forever necessarily. But so if increasing, I keep losing my mouse, sorry guys. Oh, okay. If increasing beta 0 by 1 causes the loss to grow by 2, then basically we would say that this partial derivative of the loss with respect to beta 0 is 2. If increasing this weight causes the loss to go down by 1/2, then we would say that this gradient is -1/2. Okay. And so the question is, can we calculate all of these partial derivatives for this complex expression here? So if you do it by hand on the whole thing, you get this big, long, complicated thing. All right. And I think there's slides that break this down into smaller steps. Yeah. So what we're going to do is we're going to write this as intermediate calculations instead of trying to do this in one giant step. Okay. So what we're going to say is we have our first function, f0, which is beta 0 plus w omega 0 times x, right? And then our next function, h, is just taking the sign of that. And then the next thing is we multiply by the weight and add the bias. We take e to that power. We multiply by weight and a bias, take cosine of that. Multiply weight and add a bias. And then our loss function is just the square of the difference between that and the actual label. So for a given x and its label, its actual value, sorry, actual, gosh, I keep losing my mouse, sorry. This is the loss function. So essentially, now what we've done is we've broken this down into individual steps, and you can see the loss is here on the right. That's the final thing we're going to calculate. If you have all the other pieces, you can just run F3. I'm sorry, guys, but my mouse just keeps disappearing. I don't know. Change it. All right, I'm not going to fuss with it. All right, so if we knew everything else, then if we knew everything else, then from F3, basically we can compute the loss and we can compute the impact on it. But in order to do that, what you need is you need H3, and then in order for that, what you need is F2. So again, here we don't have multiple nodes, and so this is just a straight line. There's no branching here, okay? So this is our simplest possible example. And so what we're going to show is how basically you can work backwards from the loss, calculating a bunch of things in order to get all of the partial derivatives, which in this case means how much each thing contributes towards the loss. And again, this is like a complex thing. Like just imagine that you've got 4 people in the kitchen and they're all helping to make dinner. It's not that easy to say, like, how much did each person contribute towards dinner being done? Is this person did 1/3, this person did 1/4, like, but mathematically with functions, we can do something along those lines where we're trying to identify an exact numerical contribution for each portion of it. So in the backward pass, what we're doing is we're saying from our loss, okay, which is basically again, we take our prediction minus the actual, square it. Using calculus, we know that basically if you have a particular value here, you square it, then basically how much does that contribute towards this loss? So we need to know how much the loss varies as a function of F3. And then from that, in order to calculate that, we'll need to know like how much is loss function from H3 and so on and so forth. So what we're doing is we're doing all these intermediate quantities and we're going from right to left. So in this case, the first of these derivatives, so this is the loss function right here, F3 minus our actual value y, quantity squared. If you want to know what the partial derivative with respect to F3, for those of you who know your calculus, it's going to be 2 times F3 minus our value y. So we can have a closed form equation for what this is. So for a given value of F3 and a given value of our label y, basically this partial derivative, we have an actual number. Okay, so when we're going through our training examples, if the label for a particular thing is 1 and our prediction is 1/2, then this is going to be 1 minus 1/2 squared quarter times 2. So the partial derivative del loss del F3 is going to be 0.5. All right, it's going to always be an actual number when you finally do this. But we have the closed form equation for this, and so when you're running, say, PyTorch code, PyTorch basically knows that I'm going to calculate this expression, 2 times my prediction minus the actual value, and that will be our gradient. So once you know this, then we have this formula that says the loss with respect to H3, this is again multivariable calculus, is this expression, okay? This is sort of the chain rule in action, okay? So it's the partial derivative of F3 with respect to H3 times the partial derivative of the loss with respect to F3. I'm not going to go through all this, but the key thing to note is that this right-hand side here, loss with respect to F3, is exactly what we just calculated in the previous step. So what we're going to do is in this next step, if we have that number and that number is 0.5, then all we need to do is say it's this, calculate this expression, multiply it by 0.5. Once we calculate this, and let's say this number is -1, all right, then when we go to the next step, okay, so here's the part where they say it's already computed. We go to the next step, we're going to already have our -1, and then we're going to have to multiply it by this other piece here. And let's say this works out to 2. So then for this next one, we're going to know this part in parentheses is already 2, and we're going to calculate just this one part. And this, let's say, comes out to 0.3. Now we know that this part in parentheses is 0.3, and we just need to calculate this little part. So I don't know if I've done a great job explaining this, but hopefully you guys have either already been exposed to backpropagation, or at least this gives you some intuition as to why when you're calculating the partial derivatives, the gradients for the earlier layers, it's not this gigantic calculation, but rather all it is a small calculation on top of the things that you already calculated for the layer that's to your right. All right. So then there's a whole bunch more math, but that's basically the intuition, is that if you're going from right to left as the diagram's being drawn, that each layer further to the left just requires doing a little bit of calculation and multiplying it by the values that you've already calculated for the later layers. Now there's one more step, okay? So we said that we were calculating how much the loss changed with respect to F3, H3, F2, H2, okay? But those aren't actually our parameters. Those are just these intermediate functions. Our actual parameters are the omegas and the betas, okay? So this diagram shows that previously, if we calculated this whole chain, and I don't remember what I said, but I said this is 0.5, this is -1, this is 0.3, right? We still need to calculate the slope, the gradient, the partial derivative with respect to this. And so there's another expression here, okay? In this case, for omega-3, what we need to calculate is this partial derivative. How does F3 change with respect to omega-3? And then once we've calculated that, we can multiply that by our 0.5. And the same thing here for beta-3. And then if this one's 0.3, we calculate this partial derivative multiplied by 0.3. And so then ultimately, what we will have, what you see here on the slide is the formulas, but what you will actually have are actual numbers. So this number here will be, 0.25. This number here will be 0.1. This will be whatever, 0.3. And those are all of your gradients. And so in our gradient descent formula, let's say alpha is 0.1. If we say we're going to take a step, then what we do is we multiply all of these numbers by 0.1 because we want to take a small step, and then we subtract that. So I think, I don't remember what I said. If this number is 0.2, okay, you multiply that by 0.1, you get 0.02. So we're going to subtract 0.02 from the current value of omega-3. So if omega-3 started out as whatever, 0.1, we're going to subtract 0.02 from it, and it's now going to be 0.08 in the next time step, in the next iteration. So again, you see a lot of formulas here, but when PyTorch is actually running this code, it's calculating numbers. It's not dealing with this symbolically. The symbols here help us understand the calculus that was used to derive the formulas, but ultimately what PyTorch is doing is it's just getting a bunch of numbers. And eventually, like I said, you will have a gradient for each parameter. We'll multiply it by our learning rate alpha, and we'll subtract that. And then hopefully what happens is we're moving in a good direction. And so the next set of things we calculate will have a smaller loss. And we keep doing this until the loss converges or some other stopping condition that we've decided for our gradient descent algorithm. All right, I think there's a bunch more slides, but I don't know if there's too much more to talk about. So let me just pause here, having gone through the toy example, where again, we don't have vectors, we don't have multiple nodes. But any questions just about this idea that, hey, with calculus, you can do this iterative calculation, and it's a relatively small calculation that you then multiply by numbers that you've already calculated, and that you never have to do some single ginormous calculation in order to figure out. So it's a very efficient algorithm as long as you have enough memory to store all of the things that you've calculated from the previous step. All
Hey,
right,
Ted, I have a quick question.
please.
Uh, you know, yes, it's very basic. It's a basic question. I mean, how do you construct the cost function as sine exponential? Is that one type of math representation for the gradients that you talked before, or there's more, concepts behind that?
Yeah, so in this case, the author used sine, cosine, exponential, because they're functions you've probably heard of. Those are not very realistic examples for neural network learning, okay? Typically, what you see in neural networks is you multiply it by a constant, so those are your weights. You add a constant, those are your biases. And then things like ReLU are our activation functions. And so I think there's a slide here up ahead that will say what's the gradient for a ReLU function, okay? Which is whatever. It's not that hard, but it's a little bit more complicated. Most people have already seen in calculus what the derivative of the sine function is, and they know that it's cosine. So that's why the author picked it for the toy example. But hopefully that doesn't confuse you, because that's not a very realistic realistic example
Okay,
for neural
thanks.
network. Yeah.
I think author pick up these functions because they look like a function in front with parentheses. So it's very convenient in a formula when you do it. ReLU is not very convenient because there are, well, I don't remember any particular notation for ReLU in such form, for example, and besides it is piecewise, which for some reason is requires a bit of a well, my students, I remember, didn't like piecewise functions. They saw them as unnatural.
Exactly. Yes. So sign is continuous everywhere, defined everywhere. So it's just an easier thing for us to not have to have like footnotes and asterisks and stuff like that. All right. So I think I'm going to kind of whip
So
through
what
the
is a
rest of this.
typical cost function?
So there's two things to it. Okay. There's activation functions. And so different forms of ReLU are pretty much what everybody uses these days. So they might use curvier ones, okay? But basically it's something akin to ReLU where it's very flat for numbers less than 0, and it's approximately y equals x, slope 1 for values greater than 0.
Yes, derivative
Okay.
is very easy to compute, and you do not add much of the computation errors when you do it. I mean, you don't add any computation errors when you do it, when you compute it.
Yeah, thank you, Maya. Yes, and so thanks for putting in the chat. So I'm using the author's slides, which are on his UDL book GitHub. That is correct. Okay, so eventually he's got a bunch of slides that say we can sort of do the same thing, but with vectors and matrices instead of with scalar numbers for the sake of time, and also because I don't think it helps with the intuition. What you need to know is that if you were able to follow that example and you replace the sign with any other function you want, it could be the square function, it could be a ReLU function, it could be square root, could be anything. Okay, then you can do the same thing on, say, 4 numbers at the same time instead of 1 at a time. All right, so you're just replacing scalars with a vector. And if you want to multiply all these numbers, then you need to multiply it by a matrix or a vector or whatever. So it's a notational thing, but then otherwise the equations kind of look the same. So if you have a matrix that is 4 by 3, then basically to get partial derivatives, your gradient here, you're going to need a 4 by 3 matrix of gradients. Because again, you need one gradient for each number that you have. So again, if this number's, this number's 0.1, the gradient's, 0.02, or sorry, times alpha is 0.02, then we're going to subtract that. We're going to get 0.08. So I'm going to just go through these slides pretty quickly here. But what you can see is for scalars, we have this formula, and then in whatever vector calculus notation, when you have a vector or a matrix, you use bold. So basically, we just switch from a regular beta to a bold beta, and this means that this is actually a vector of more than one number instead of just a single real. This omega with a capital letter is capitals, generally speaking, are matrices instead of vectors. And it's bold, but otherwise the formula kind of looks the same. It's just we have slightly different notation. And that's sort of the beauty of multivariable calculus, is that you can kind of do everything that you learned in regular calculus, just throw in vectors and matrices instead of scalar numbers. All right. So talks about the forward pass, backward pass. And again, it's just the same concept that if you've calculated gradients for a particular layer, there's only a small amount of additional work you need to do to calculate the gradients for this layer, because you've already saved off these numbers.
What was yikes? Oops.
I don't know. All right. So here's our ReLU function. So you can see the actual ReLU function as opposed to some of its similar curvy variants. is just 0 for everything less than 0. So the gradient of this is 0. There is no slope. This is a horizontal line. And the gradient for everything greater than 0 is 1. This is a line of slope 1. So essentially, the derivative of the ReLU function is shown in this light blue, blue-green, teal color, okay? The derivative of the brown ReLU function is 0 to the left, and it's 1 everywhere to the right. All right. And you can look for some fancy mathematical notation to describe this because it's piecewise, okay? And they give it in the book. They have this capital I indicator function, all right? So capital double I indicator function says, hey, if z is greater than 0, this thing is true, this thing is 1, otherwise it's 0. So if indicator function works for you, great. If it doesn't work for you, you can just imagine that you calculate all results for negative values using one function, and you calculate everything for positive values using a different function. And you just use an if-else slapped in there, okay? Ultimately, that's kind of what the indicator is doing anyway. So whichever intuition works better for you. The bottom line, though, is that there is a derivative, there is a gradient everywhere. It's just that it's calculated piecewise. All right. So for time, I think I'm just going to kind of blitz through the rest of this just to say again, if multiplying has a derivative, adding has a derivative, and ReLU has a derivative, then you can always combine them. You can composite them. And through multiple steps, you can see that, again, you can work your way backwards from the loss all the way towards your inputs. And there is formal mathematical notation that says how you do all this, but the important thing is just to know that modern times, you're using TensorFlow, you're using PyTorch, it's going to do all of this work for you. This is just for you to understand the intuition behind that there is formal math that says, hey, my loss was 10. I need to figure out what the relative contribution was for each of my weights and each of my biases. And I also need to know, like, if we're getting a big contribution, like if I change this weight, would my loss change a lot? Or in some cases, if I change this weight, the loss would change very little. So if it's a lot, then that means you have a big gradient, and that means that we want to take a bigger step in reducing the value of this weight. Whereas something that has very little or even say 0 impact on our loss, then we're not going to, when we do gradient descent, we're not going to take a big step on changing that weight. All right, so pros and cons. This is a very efficient algorithm where you kind of go from right to left, and for a standard neural network, you're just doing matrix multiplication and ReLU, and the derivatives of these are very easy to calculate. The only issue is it's memory hungry. You need to sort of store all of this information in the forward pass, and then you need to be tabulating your values as you go from right to left. Okay. It also mentions that it's sequential, so that if for some reason, like it was taking you a long time to do the backprop going from right to left, then basically you're not doing anything else with your computer until you sort of finish doing all of this. So potentially, if you were underutilizing your computer's resources, you could try to process multiple things in parallel. I think generally speaking, that's not a problem. Our models these days get very big, and so when you're doing these ginormous matrices for these large neural networks, that actually takes your GPU a long time to calculate everything. So you're actually keeping it fairly busy. All right, not going to say much about this except that basically these steps going from right to left are implemented into TensorFlow or implemented into PyTorch, And so you can take advantage of automatic differentiation. So basically, you define your weights, your biases as parameters, and basically in these libraries, you can say you can call the backward function, and it will basically at that point calculate your loss, and it'll calculate all the partial derivatives for all of your parameters. You don't need to do any of that legwork. All right, the author has some sample code. We might talk about that, but I want to get to the second half of the chapter, which doesn't take too long. So I'm going to flip over to this other deck. So talking about initialization, really, he says in the book, I think this is the intuition, that if your weights were, let's say, 5 everywhere throughout your neural network, then you can see that if you start with an input of 1, you're going to have an output that's somewhere around 5. I mean, maybe it's 10, maybe it's 15 if you have multiple nodes, but it's going to get bigger. And if then the next layer has weights that are all around 5, then your output's going to be at least 25. And again, it might even be bigger if you have multiple things summed. All right. And then another layer of 5, 125, so on and so forth. So if all of your weights were on that order, what's going to happen is your outputs are going to be getting a lot bigger. And in addition to that, your gradients are also going to be getting a lot bigger. And so mathematically, there's technically nothing wrong with that. But with just our computers and our floating point notation, we may have some problems. We may have some problems with what they call exploding gradients. On the flip side, if all of your weights were less than 1, so like say 0.1, you could imagine that you start with an input of 1, maybe the next output is 0.1, maybe it's 0.2, whatever. And then you go through another layer, maybe you're now down to 0.02, and then 0.001, and then 0.0002. And so your values are getting smaller and smaller and smaller. And again, not only your values getting smaller, but your gradients are getting smaller. And so then this can also cause a problem, again, with our floating point numbering system. Technically, if you didn't have approximate numbers in floating point, if you had, perfect precision, wouldn't necessarily be a problem. But because we're using approximate numbers, we're using floating point notation, this is a problem. And so what we want is essentially for our numbers to stay kind of in a fairly bounded range. And typically what you're going to see is the idea of maybe we want mean 0, variance 1 as a very standard way of representing things. So it's pretty easy to say then, oh, okay, if I have a particular kind of network where I multiply by so many weights, how big or small on average do those weights need to be in order for my output value to continue to be approximately mean 0, variance 1? And I don't remember what's in the slides exactly, but basically, is there a diagram? No, this has a bunch of math. What I wanted to do is to say, if we look at this neural network, okay, the more nodes there are to your right, the more copies of your output you're going to be passing on. And so it turns out that basically the more nodes you have on your right, sort of the bigger things are going to get, is a simple intuition. So right here, this layer you see has 2 nodes. And so for each of these 4 things, the output gets sent there twice and ultimately, gets weighted and summed. But if instead of 2, we had 200 nodes, then this single output from here would be getting copied 200 times. And then the total effect going into this next layer of 3 nodes would be much, much, much bigger. And so that's the intuition why ultimately you're going to see in our initialization formulas, what we're going to do is we're going to want to scale things based on how many nodes that you have. Because when you have more nodes, that actually causes you to do more multiplies and that's the gist of it. So there's a whole bunch of things here on like statistical expectation and variance and whatever. But I'm pretty sure we're going to get to, where is it? Come on. Sorry. Okay. So basically this D here is I think the degree, the number of nodes in the next layer. And so basically what we need to do is we need to make sure that we are the reason why we're dividing by this is because of this impact where the more nodes you have, the more it blows up things. So if you're zero mean, things stay zero mean, but your variance is going to get bigger the more times that you multiply it and add it together. And so Kai-Ming He came up with this particular, there's default initializations for fully connected layers, for CNN layers, so you don't really have to worry about it. Generally speaking, you're going to use the default initialization, okay? But basically that's the key thing here is understanding. In the book, there's a formula that shows so you get this effect in terms of how many nodes there are in the layer after you when you are doing the forward pass, but you get sort of the reverse effect when you're calculating gradients, where it's the number of nodes that are to the left of you, okay? So there's this compromise that people have come up with where they say, oh, well, why don't I just sort of average the number of nodes before me and the number of nodes after me. Okay. I wanted to mention, just because this is one of my favorite ML papers, and it doesn't seem to be like that super everybody else's favorite paper, but Greg Yang did this paper. It has kind of a weird title. It's called Tensor Programs 5. It's the 5th paper in a series of papers that he did. And one of the things that he said, which I think is really cool, and somehow nobody seems to have latched onto it. But when we talk about a learning rate, an alpha like 0.1, what we say is you calculate the gradients on all your parameters, and then I'm going to multiply all those gradients by 0.1 and subtract them from the relative parameter. What you could do is you could have a different learning rate for each layer. And so basically what in this Tensor Programs 5 paper, what Greg Yang says is what you can do is based on the number of nodes coming in, if it's bigger, then you use a smaller learning rate. If it's smaller, you use a bigger learning rate. And you can basically normalize the gradients based on how many nodes there are in your adjacent layer. Okay, I'm oversimplifying a little bit, but the general idea is you don't necessarily have to do this approximation math business. You can use the regular initialization, and then because if the number of input nodes and the number of output nodes for your layer are not equal, then what you can do is you can just apply a custom learning rate to adjust for the difference in the number of nodes. And I actually thought that that was a really, really cool thing. And I just haven't seen anybody implementing that in like PyTorch or TensorFlow. But in theory, what that should allow your networks to do is to train a lot faster. Might introduce some other problems, and maybe that's why people don't use it. But it will pretty much guarantee. There's other things that people do, so you'll hear about like batch norm, layer norm, and that might be part of the reason why people don't need this. But in general, I thought that was a really cool thing, and it's not covered by the book. And that paper's like 2 years old at this point, I think. So it's not like it's brand new. All right, so I hope that was helpful. Like I said at the very beginning, I felt like this chapter was much more math heavy, less on the intuition. Many of you, I expect, are familiar with back propagation, but hopefully this helped solidify your background, your intuition on what's going on there. And for those of you who don't know, like the calculus, the multivariable calculus, it's enough to give you an intuition, since you don't have to actually calculate these on your own. The libraries, PyTorch, TensorFlow, they'll do it all for you.